So in the numerical RTA workflow, before you start to interpret this Bowie diagnostic plot right here, or the numerical RTA diagnostic plot, by moving this line up and down, which is essentially changing your A root K, right? This parameter here to the left. And then picking an associated type curve, which is picking the pore volume here, the contacted pore volume. Those two items, before you go ahead and decide on those two items for a given well, you need to make sure that you've checked for two items in particular. And those two items are, is my water cuts making sense, and is my GORs making sense, okay? So those practical aspects I'll cover here in a quick presentation. First thing to just emphasize is what are actually the inputs to numerical RTA? Well, there's a lot of inputs to numerical RTA, but in addition to the flow rates and pressures, we have PVT, which is an important input, water saturation, relative permeabilities, fracture conductivity, geomechanical effects, and rock compressibility. Okay, so what does that mean? That means that if I change any of these inputs, I actually will have to go in and rerun the model. So I have to go in and click run again at the bottom up here to the left to regenerate my curves. Okay, but any of these parameters right here in the gray area, they're actually outputs from the analysis because you're interpreting what an A root K is, you're interpreting an OIP, and when you have those, you can also resolve, for instance, a matrix permeability and fracture half-length, for instance. So just to make that extremely clear, if you update any of the items below, essentially here, dimension fracture conductivity and down, including the rel perms, you'll have to go in and rerun the model. But everything from here and up, you don't have to rerun the model. Okay, so that's just a quick reminder what is actually the inputs to numerical RTA. But if all of that is good, you need to check for two things before interpreting the plot. The first thing, you should check for stabilized water cuts. So are you actually matching the stabilized water cuts from the well? The second thing is, are you actually matching, or are your GORs, or is your GOR match making sense? And once you've made those two checks, you can go ahead and interpret the plot. But what does that really mean? Well, for the water cuts, stabilized water cuts is what we interpret to be kind of the formation water. So what is actually the formation contributing in terms of water production? And that means that we're ignoring this early time flowback water right here, which comes from the completion exercise. On the GOR plot, on the GOR side, we're keen on making sure that we match the initial producing GOR, which will be equal to the solution GOR. And once we go below saturation pressure and our GOR starts to kick up, that happens around the same time in real life and as in our models. Okay, and that's a function of your PVT, your bottom hole pressure profile, and sometimes also what fracture parameters you assign to your model. Okay, and once we go below the saturation pressure and we see an increase in GOR, that increase is also a function of the flow regime. So if you have a big OIP versus a small OIP, or a big tank versus a small tank, that will provide us with different GOR forecast. Okay, so this will be a big one, and this will be a small one. And then once we're up, we've checked for these two things, we can then go ahead and interpret our Bowie diagnostic plot and essentially find an LFP and find the OIP stem that's closest to our observed data. Okay, so let's take a look at one actual example here. So the first thing we should go ahead and do is to scroll down to make sure that our water cuts are matched. And in our actual example here, we need to go down here and see, is our stabilized water cuts matching what my models is making? And in this case, I'm running 5 different type curves, and they are on a generic basis decent here for the stabilized water cuts. Okay, and we ignore the early time water cuts and we focus on the stabilized water cuts. But how can we, if we're not matching our water cuts, what can we actually change to make sure that we match these? Well, there's a few different things we can do. First of all, you need to make sure that your initial water saturation is correct. But once that's done, you can change some of the rel parameters, for instance, the Connaught water saturation and the water relative perm exponents, to either increase water production or decrease water production. Okay, and in the rel perms, of course, if you increase water saturation, there'll be more water production on a relative basis, and vice versa. And on the rel perm side, if you decrease or increase your Connaught water saturation, what will happen in reality is if you decrease it, you'll produce more. There will be more mobile waters. Your water cuts will go up, and vice versa. And there's also some hints here in the software that will provide you with guidance of how to change your exponents as well to make sure that you get a water cut behavior that you're also observing in the field. The second thing is on the GOR side of things. We want to make sure that we match the GOR performance before we hit the saturation pressure, and once we hit the saturation pressure, that we have something consistent also after that. So the first part of the data is while the bottom pressure is above the saturation pressure, then we should have a producing GOR that's equal to the solution GOR if we're dealing with an oil reservoir, or the solution CGR if we're dealing with a gas reservoir. This is also sometimes called this vaporized oil ratio. Okay. And then as we go below the saturation pressure, there's actually so many different reservoir parameters that can impact your GOR performance. But in short, it's relative probabilities is important, geomechanical effects is important, fracture conductivity is important, and of course the flow regime itself. So here you see different tank sizes. This is very much into boundary. This is less into boundary, and here we have everything in between. And the more you go into boundary and the more boundary effects you're observing, the higher your GOR is on a relative basis, at least for this model. But once you've made sure that your GOR is flattened and it kind of kicks up at the same time as you see in the model, and your GOR, I guess your GOR span here is also observed in the real data, you're actually off to the races to do the interpretation, which is the last step. Okay, so you've checked that the water cuts make sense, and you've gone to the right here to make sure that your GOR makes sense. So now you're actually set and ready to go ahead and interpret this particular plot right here. And when you interpret that plot, you move this line up and down, which is just how to change your A root K. And then you can do that by either moving the line up and down, or you can change that parameter right here to the left. Once you're done with that, you pick the closest OIP stem. This can be done by clicking the stem itself, or you can just type in the number here to the left. Once you've done that, you've essentially done your RTA work. The last thing you would like to do is to make sure that your CUMES at end of history here is doing a good job. As you see here for this type curve, we're doing great on oil and also very good on gas as well. And for gas, most of these type curves are very similar. And if we look at that in the software, if I did the interpretation for this guy right here, and I double clicked the legend, that's the only part of the data that we actually observe, we'll see that if I bring this into a numerical model now, I'll have a perfect history match on my CUMES, and also very good history match on my relative rates. I'm matching the stabilized water cuts, and I can say that I've done a very, very good analysis for this particular one.